So welcome everyone. This is the second session of the linear regression masterclass with Nitin. Uh, if you've already attended the first session, then you probably don't need an introduction. But anyways, my name is Ashit Dharwal. Uh, I am a civil engineer by profession, and I've been a data scientist for 2 years now at Piramal Finance. And Nitin, you want to introduce yourself?
Yeah, so guys, uh, I have my MSc in Applied Statistics from IIT Bombay, and I've been also in data science and AI industry from last 2 years, specifically working in AI ML deep learning. So yeah, we'll start with the multiple linear regression in this session.
Sure. I'll stop sharing my screen. You can share your screen. Yeah.
Just
So we are going to cover multilinear regression and hypothesis testing, right?
yeah.
Cool.
Second. Oh, my screen is visible, right?
Yes. The PDF.
Yeah, fine. So guys, in this session, we will start with the multiple linear regression. So like in the last session, we talked about the simple linear regression, and we saw what are the interpretation of parameter, how we actually estimate A and B. Specifically, we are talking about the simple linear regression. Then we also saw some evaluation metric like root mean square error, then mean absolute error. Then we have R square, adjusted R square, and we also saw like what are the difference between these, what are the scenarios where you should use RMSE or R square, adjusted R square. And we also saw the practical implementation of simple linear regression in Python. So basically we will extend this particular thing to extend understand how the multiple linear regression come into the picture and what are its use cases. So we will start with this particular basics of multiple linear regression. So basically, first of all, we will try to understand how in multiple linear regression, how the data looks like. So let's start focusing on this right hand side, specifically this particular data. So you can see that we have multiple columns here, specifically like these R&D spend, administration, marketing spend, state and profit. So it's like this profit is something that is of our interest for why, because based on the how much spend a company has done on different areas, like let's say a company has done spent some amount on R&D, administration, marketing, and its particular state, like on which state in USA it has made this particular spend and how much profit it has done. So based on all these four features, we may want to predict the profit of the particular company. But the thing is that this is not the data that we are going to use. We will be using some other data set, and basically that data set is very interesting because a lot of times those data set will help you that you can write in the project as a resume, in the resume. So that data set that we are going to see in the practical section is about insurance payout. So whenever you buy a insurance, you have to pay a premium. So we will see like how we can predict the premium of an insurance based on different features. So we will see that particular thing, but before starting, let's understand this particular data and let's understand how a multiple linear regression actually is done. So we know that in the simple linear regression we had basically x and y, but now instead of x we have x1, x2, x3. So there are different features, and these different features are actually basically based on these features we need to model this particular y, and that is why and here we have p number of independent features. So p can be in number, it can be, let's say, if there are two features also, there are three features also. So more than one features will always be the case of multiple linear regression. Now the second thing is that just try to understand the basic notations, because notations are important here. So let's say this yi, let's say we have let's say 100 rows, like let's say this particular data has 100 rows, and we have 5 columns. Okay, so we represent our first data as yi, like y1, then we have y2, something like that. Okay, then corresponding to the x, our first observation will be x11, then we'll have x12, then we have x1p. It means that we are this first indexing in the x represents the rows number, like which record are you talking about. So for the second rows it will be x21, x22, and similarly x2p. So you have to understand the basic notations of the data set, because this will help you understand your general linear regression terms later in this session. So this is very simple. We have p features, that is what the second indexing is all about, and we have, let's say, n rows, that is what the first indexing is all about. So your data will something looks like this particular kind. So your multiple linear regression model for the ith rows will be something like this. So yi is equal to beta naught plus beta 1 xi1, beta 2 xi2, plus dot dot beta p xip plus epsilon I. Because we have I is equal to n observations, but now you should understand this different observations. Like first of all, yi is called dependent variable, that we also discussed yesterday on the last session. This is called dependent variable. These x all are called explanatory, or what you can say, independent variable. This beta naught is called intercept. Still it's the intercept, because we are talking about more than one features, but yet beta naught is still intercept. And this beta p, whatever the coefficient that we are going to estimate, these are all called the slope coefficient for the each explanatory variable. So let's say you have x1 to xp, so for each of these particular predictor variables you are going to have a beta, like beta 1 plus x1 plus beta 2, something like beta p plus xp. So these are called the slope for this particular random predictor variables. So basically this is what we also have seen in the linear regression, simple linear regression, because there we have only two terms, y is equal to a plus bx. So here we called a as the intercept and b as the slope, but this is not a line in two dimension. It is generally a hyperplane in the what you can say, in the like more than three dimensions. So this is the p-dimensional hyperplane we are talking about. But this is not about the visualization. You saw the visualization in the, we can only visualize any linear regression either two or three dimensional. Once we cross the three dimensional thing, we will not be able to plot it unless we use some other dimensional reduction technique. So this is in general will be a hyperplane in the hyperdimension. So this EI is called the error term, and still we have the error term. And what we need to do this, we need to estimate this beta naught, beta 1, beta p, which are also called the regression coefficient. So overall, the thing is that now our model is yi is equal to this. This we are talking about if we want to write this model for the ith rows of the data. But in general, this is y is equal to beta naught plus beta 1 x1 plus beta 2 x2, and whatever the number of variables are, you will have beta p xp. So this is the simple linear regression, sorry, multiple linear regression model.
If I
And
can summarize a bit,
yeah,
so basically this equation, if anyone is lost right now, if let's say we have an Excel file, or you have the data in Excel, right? You have 10,000 rows. So just pick any one row. This is the equation for that. So just pick one of the rows. The y variable is the left hand side of the equation. The right hand side of the equation is basically summation of all the x variables multiplied by a coefficient. And there is an error term because no line will exactly fit each of the points. So the difference between the actual value of y and the predicted value of y is actually the error term. So this equation can be written down for all the rows of the data, but the beta coefficients will be the same for each row. That's our
yeah.
objective. The error term will be different for each row. The x's will be different for each row. Y will be different for each row, but the beta will be the same for each row. If there are any doubts, you can always ask in the chat.
So it's just like once you estimated the model, you can use the same estimate beta 1 to beta p to predict the predictions for any rows, any training rows or any test rows also. So in general, let's say you want to predict for 10 observations, so that will be your y1, y2, something like that. Y1 hat actually, y2 hat, something like y10 hat. So these are what I in general terms means. So basically this will be clear more from the matrix representation of this particular model. So in like I told you y is equal to like yi is equal to beta naught plus beta 1 x I 1, something like that we have. But if you want to summarize this particular model, like for all the records that you have in the training set or in the data, you can write it as in the form of the matrix representation of this particular model. So what this matrix representation means, so this is basically, this y is not a this is not a number, it's not a scalar term. This y is a vector actually. This vector looks like this. So like we have, let's say we have n rows in our data set, and let's say we have p columns. Okay, so how do you write in the form matrix particular this model? So y is equal to x beta plus epsilon. So this epsilon is also not a fixed term, it's also a vector. So if this is how we write, but this is what in general it means. So y is a vector from y1 to yn. So basically this y has 1 to total n cross 1. This is the shape of the y. Now x will have total let's say it has a k number of features, so let's not represent it p, let it be k. So it will have n cross k. So these are having n rows and k columns. So this may be the first predictor, this may be the second predictor, similarly this may be the kth predictor. We add 1 in the x because we also want to estimate this beta naught. So beta naught does not have any predictor because this is a constant term. So that is why we have a columns of unit vector also in the x that represent that this will correspond to whatever, whenever you want to estimate the beta naught, this will correspond to this particular thing.
We
Now
have a question. Someone is asking, I thought vector is a matrix with either only one row or one column. So X is also a vector.
X is not a vector, X is a matrix. So Y is a vector, the beta is a vector, this epsilon is a vector, but this X is a matrix of n cross k. So this beta is a vector, and this epsilon is also a vector. Now let's say if you want to combine this, all this particular thing, will it result in the same model that we saw earlier? So let's take a look on that and let's try to combine all this to see if it actually results in whatever we saw earlier. So now let's say we multiply x plus with beta. So we will write here beta because we're multiplying x with beta. So let's say this is our x and this is our beta that you want to multiply. So this will be beta 1 dot dot beta k. So if you multiply this, so multiplication in the matrix goes like this particular thing will be multiplied with this. So this will basically will be resultant as beta naught plus beta 1 x11 plus similarly beta k x1k. Here it will be beta naught plus beta 1 x21, and similarly in the last your last entry will be just give me 1 minute. Yeah, so last entry will be your beta naught plus beta 1 x n1 plus like similarly. So you can say that now our y1 means we have y is equal to x beta plus epsilon. Now we will add epsilon. Then similarly your entire model will become y1 is equal to this term, y2 is equal to this term, and yn is equal to similarly this term. So basically this is what we started with in the initial part, generally denoting the indexing with the I. But here this is I is from 1 to n. This model is in general with the I from 1 to n because we have n rows in our data. So it means that we can represent our model in the form of the vector and matrices also. We can represent our model in the form of this particular thing like we initially explained yi is equal to something like that. But this matrix representation is very compact representation of the model, and it will help you like do the calculations very easily, especially if you are doing the computation. So now one may ask you, okay, this may be the representation of the model, then how we are going to estimate this beta naught if we are going to represent this particular thing in the matrix form? So earlier I will tell you how to estimate the beta, but first of all let's understand the assumptions. So in the last section or last session also I explained the assumptions of the model. So assumptions are going to be the same because we are anyway fitting the linear regression model. So like we have the linearity, we have the homoscedasticity, means the residuals of variance should be the same. We have the independence, like residuals should not be have serial correlation. We have normality, like this epsilon should follow normal distribution with 0 comma sigma square. So this assumptions is going to be the same for each, and still whatever we are looking right now, the model we have. But now the thing is how to estimate the beta. But yeah, before estimating the beta, let me explain to you the interpretation of beta. Like in the simple linear regression, we had just two things, like y is equal to a plus bx. We know that this is the slope and this is the this is the what you can say, this is the intercept and this is the slope. But in the regression terms, I study explained that the b is, or you can say that the coefficient of x is the amount that y will increase when x is increased by 1. So what does all this beta 1 to beta p means in the multiple linear regression? So these also have some meaning. So what is the meaning? First of all, beta naught still is the intercept parameter. It represents the value of the mean response. It means that value of y when all p are 0. So I told you specifically that yi is equal to, let's say this, right, y is equal to beta naught plus beta 1 x1, something like that. So let's say this x1 is equal to 0, x2 is equal to 0, this all xp till xp is equal to 0. Then if all the all the values are 0, then we will have y is equal to beta naught. So this is the interpretation of beta naught. Given all the predictor variables are 0, what is the prediction of y? So that is the beta naught. Now the second thing is that what is the prediction of beta j in general? Beta j means what is the prediction of beta 1, what is the prediction of interpretation of beta 2, what is the interpretation of beta 3, and so on. So in general, beta j represents the increment in the mean response when xj is increased by 1 unit. So let's say we keep all the variables constant, we just increased whatever the xj is, we increased by xj plus 1. So corresponding to this particular its coefficient will be multiplied. So our model will means the value of y will in general increased by the beta j. So this is what we also saw in the simple linear regression also. When x is increased by 1, the y gets increased by the value that is this particular coefficient. So that is why these are called partial regression coefficient. Means this, it does not mean that कि अगर हम xj को बढ़ाएंगे तो हमारा y बस बीटा j पे डिपेंड करेगा. It will not happens like that. हम लोग अगर xj को बढ़ाएंगे तो y में जो इंक्रीमेंट होगा xj की वजह से वो बीटा j अमाउंट होगा. Let's say we increase x2, then वहां पे बीटा 2 अमाउंट इंक्रीज होगा. If we increase xp in general by 1 unit, बीटा p अमाउंट इंक्रीज होगा y में. So that is what the interpretation is कि it is about कि if we increase any particular variables, y में उसके coefficient इतना increase आएगा. That is a partial increase. It's not due to all the variables because all else variable is the constant.
So basically, if someone wants to understand in the language of calculus, maybe, so you can consider this a multidimensional space, and let's say you have 10 features. So you can consider a 10-dimensional space, and you can consider beta 1 to be the slope of the hyperplane in the direction of x1.
Yeah.
In the direction of the direction of x1, if you consider a 10-dimensional space.
So it means that ki overall, in the terms of overall plane, beta 1 is just contributing in the direction of x1. That is why it is also called partial regression coefficient. And earlier in the simple linear regression, this a and b is called regression coefficient because we have only two terms. We have just x and y. We don't have any other thing. But in terms of multiple linear regression, these are called partial regression coefficient because each one have some contribution, like beta 1 to beta p, each one have some contribution in the hyperplane. So now one may ask, like, why do we call it a multiple linear regression? So it has two meanings. The first is that since we have first of all the linear, why this is a multiple linear regression, why is it linear? Because it is linear in the parameters of beta. So when you will see this particular model, you will see that this particular model is linear in parameters of beta. Like it's not like beta have some non-linear relationship with I. These all betas have linear relationship with y. Now the second thing is why it is called a multiple linear regression, because we are actually considering more than one predictor variable. So multiple linear regression means we have multiple predictor variables, and all those predictor variables, their coefficient are linear in terms of beta. So this all beta have linear relationship with y. So that is what we also see in this particular model. That's why this is called multiple linear regression. So we have multiple predictor variables, and we have linear relationship in terms of beta.
So Kanishk has a good question. Whether beta 0 plus beta 1 into x square is linear or quadratic.
Yeah, this is also linear model, because we are just considering two features. So it's just like y is equal to beta naught plus beta 1 x square. This means we just replace x square with some other variable. Let's say z is equal to x square, just for the sake of simplicity. Then you have y is equal to beta naught plus beta 1 z. So basically we are talking about a simple linear regression. So this x square is just what you have. This x square just the quadratic terms of x. But here, if you just include something like beta 2 in x, then this particular thing will have multiple regression, because we are considering two different predictor variables. Obviously, these are the same predictor variables, but x square is the transformation of x. X square is not behaving as the x is behaving. So just you are considering x square as totally new feature. So whatever this particular thing is, this is obviously the linear model. This is not non-linear. This non-linear means that in terms of beta we are talking about. If the beta is having some non-linear relationship with y, that is when we call it a non-linear model. But yeah, this y is equal to beta naught plus beta 1 x square. This simple thing is still a simple linear regression.
So basically, linear regression is all about calculating the betas or all the coefficients.
Yeah,
Really.
means the linearity we always talk about in terms of beta. We don't talk about in terms of x. Like this particular thing, if I write y is equal to beta naught plus beta 1 x1 plus beta 2 x square plus beta 3 log x, sorry, log x2. These are all having linear relationship with y. So these are just a transformation of x. This always you can replace with some other random variable. Let's say log x2 is equal to, let's say, z1. So again, we are again talking about the same thing. So this is just a transformation of your predictor variables. You can transform your predictor variables into anything, and we do. Like there is a special term that is called feature engineering. So in the feature engineering, what we do, we combine different features to create new features. Like we may use some transformation, we may use addition, subtraction, or any particular operations on two variables to create a third variable. So that is the same thing. So it is not going to be non-linear regression. It is still be the linear regression, and we're still talking about the linear model.
Also, sometimes people may get confused when they see x square, and they might think that this might not be linear regression, because whenever we used to study maths in high school, so we used to study quadratic equations, and whenever, let's say, we study a parabola, so let's say we study y equals to ax square, so they call it a quadratic equation, but that is in x. There, a is a constant that is already known, and x is the variable. Uh, here, the coefficient, that is, if you see y equal to a plus bx square, so here a and b are the ones that we have to find out.
Yeah,
So
these are
that's why we,
these are the, here you can say that these are variable here. X we know, y we know, but a and b want to estimate from the data.
yeah. So if you already have the data set, you already know x and y. You have many x's and y's, but you have to calculate a and b. So here the linearity is in the terms of the coefficients.
One more thing, like someone is asking, in scalar we have polynomial option available. Yeah, we can go for the quadratic linear regression also, but that is the multiple linear regression. We are actually talking about the quadratic features, like x square is the quadratic features of x. So those are called polynomial linear regression also. But yeah, those are all the case of linear regression. So one may ask, like, how do we estimate the beta? So in general, like beta hat, if we represent, this is just the vector of the beta. So here we are talking about beta naught, beta 1, beta 2, and beta p. So, this quantity that I have written in the green box, this is called y minus x beta hat. This y here is the vector, and y minus x beta hat transpose y minus x beta. So this is exactly the error का square जो we were talking about in the simple linear regression, this is the same thing. So but hence there here we are talking about the matrices and vector, so we don't actually write like E square, we just write E transpose E. This simply means that in if you're talking about the scalar thing, it simply means the E square only. So when you will try to minimize this particular quantity, so this involves like doing differentiation in the terms of matrices and determinant. That is actually a very high level thing. So if you do this, differentiate it in the terms of beta to estimate the beta, you will get this particular quantity, which is called the estimate of beta, and we represent it as a beta hat. So when you will calculate this particular quantity, it is not a single number. It will be the form of a vector, and it will give you estimate of beta naught, beta 1 hat, similarly beta p hat. So it will give you the estimate of all those things at once, and this is called x transpose x inverse x transpose y. This is called the estimate of beta. So this is one of the fact that you can remember, but this always can be proven, and this will be proved when we will try to minimize this particular quantity. And when we try to minimize this particular quantity, actually you have to do differentiation, integration, sorry, not integration, differentiation in terms of the matrices and vector. So like differentiation of matrices and vector works a little bit different than we differentiate a simple particular function. Let's say we want to differentiate x square, or maybe want to differentiate x cube plus 2x plus 1. So this particular matrices differentiation works a little bit different. But yeah, if you just try to differentiate it and equate with 0, you will get this particular quantity, which is called the estimate of beta. I think so. Right now, what we have seen, let me just have a very quick recap. So we have seen how our data looks like in the multiple linear regression. So basically, for if we have n rows, we can write the model in the form of indexing with yi. So yi is equal to beta naught plus beta 1 x I1, something like that. But if you want to like make a compact representation of this model in terms of matrices, we can always do. So this x is what we assume this is n cross k matrix if you have k features, n cross p if it is a p features. Y is the vector, beta is a vector, and epsilon is a vector, and this is what y is equal to x beta plus epsilon looks like. Now these are the assumptions that we also talked in the last session. Assumptions are fairly same, and now we have talked about the interpretation of beta, basically partial regression coefficient, that each coefficient have certain contribution in value of y. That is why they are called partial regression coefficient. Now we have justification of linear model, like why this is called multiple linear regression, because you have multiple predictor, and this particular model is the linear in the parameters of beta. Then we talked about the estimating beta. So basically we try to minimize this particular error square, and this is also called the method of least square. So this is still the method of least square, but we are talking about in the term of matrices and vector. But in the last session I explained like how the method of least square can be understood intuitively. So this is a, if this is a regression line, and let's say these particular points are your real data point, so basically you calculate the difference and you try to minimize this squared sum error. And when you will try to minimize this squared sum error of this particular thing, this method is called method of least square. And similarly here we are also doing the same thing. We're trying to minimize the squared sum error of the particular model, but generally we are representing in the form of overall matrices and vector, but this contains the same thing that here we in the beginning we wanted to minimize. Now the question is, once you fit the model, we represent beta hat. So beta hat is basically the beta naught hat, beta 1 hat. So these are all the estimates. So we generally in the statistics represent the estimate in the terms of hat, like beta naught hat means it is the estimated coefficient of beta, and beta 1 hat means it's the estimated form of the beta 1. So once we can write your model as this one. So let's say if you want to make a predictions for a particular value of x, so let's say x is equal to let's say 1 comma 2 comma dot 7. So this may be the p cross 1 vector. So what you need to do, just try to plug in here 1, plug in here 2, and similarly plug in here 7, multiply with this particular coefficient, and this will be your y hat predicted value. So this is how your multiple linear regression makes the predictions on the test data once you have estimated beta 1, beta 2, and beta p. Let's say and that is what we also call the fitted value. So let's say if you want to represent the fitted value of particular ith rows of the data, you can do the same, like put the ith value, put the xi1, and similarly you can get this particular thing for the training data. But yeah, the thing is that once you have the model, now you can calculate the residual. So what is the residual? So residual means that this is basically the error term. So error means that let's say y is equal to your predicted thing, and let's say, sorry, y is the real values that you have in the data, and y hat is the predicted. So y minus y hat is called the residual. So again, this is in the term of vector we are talking about. So y here means that all the values of y that are in the data set, and this y hat means that all the value of your y hat or predicted value, if this is in this particular vector. So if you differentiate these corresponding terms, this particular things will be your error vector or error or residual, whatever you want to say. So this is what in general we have in the multiple linear regression. So if you have any questions in terms of multiple linear regression, we can take now. I see you may want to have a quick summary if you want.
MT had a question, but I don't think I understand it. Okay, why we add constant in X matrix? We add a constant column of ones. Why do we add that?
So we like in the last session, I also show you like how do you estimate your coefficient in the Python, and here there we also saw we are adding a constant vector. So this is the similar approach. We know that your y is not beta naught plus x one, sorry, beta 1 plus x1 plus beta 2 plus x2. Your model don't work like this. You have a coefficient or what you can say a constant term of beta naught. So if we do not include this one in the x, what we need to do first, we will calculate this particular thing, and then we need to calculate beta naught separately. But what we can say, we can just concatenate a vector of 1 in the x, this particular column, and when we'll try to estimate, this particular will correspond to the estimating of beta naught. Since beta naught is constant, that is why you can assume that here 1 is always multiplied, just like beta naught into 1 plus beta 1 into x1. But since x1 have some value, but this beta naught is a constant, you can assume that this 1 is always multiplied, and that is why we have included a vector of 1 here, a column of 1 here, to estimate the beta naught. And when you will find this particular estimate, it will also give you the estimate of beta naught, like we talked in this particular thing. It is always going to, you are going to find the estimate of beta naught. So just like in the simple terms, you can understand that beta naught means that beta naught into 1. So you can write here 1, and this will give you the estimate of beta naught. So this in the simple terms, you can understand it this way.
So instead of that, so he's asking for an example. So if I can give a small example, for example, let's say you have 3 features. So you will have beta 1, beta 2, beta 3. And you also want to have a beta naught, because you don't want to only get y in terms of the x's. There has to be a constant term as well for each row, basically. So you can either do this, you can either add this column of ones in the X matrix, or another way to do it is you can have a n cross 3 matrix for the x's, multiply that with beta 1, beta 2, beta 3, and add a vector of beta naughts to this whole thing. That will be an equivalent thing.
Yeah, it's going to be the same thing. So basically, this is what the final your X matrix looks like. So basically, he wants to say that, let's say we have let's say x1, x2, x11, x12, x1p. Similarly, we are not considering the one term. Then we have similarly xn1, xn2. We have n features. Okay. So what we do here, we just multiply it with beta 1 to beta p, and then we add it here, beta naught. So it is going to be the same thing. So this is going to be your y finally. But whatever we have written here, like you can just write a vector of 1 here, and you can just put the beta naught here. It is going to be the same thing. So both are the same.
Write the sizes of these matrices.
Yeah,
the
so
X
this
matrix
X is going to be n cross p.
n cross p.
This is going to be of p cross 1. And this is also going to be your p cross 1.
No, this is going to be n cross 1.
Oh yeah, sorry, n cross 1. Yeah, because we are adding to each and every rows. So basically, if you want, you can just make it unit vector here, and you can just write beta naught here. It is going to be the same thing that we discussed. I think we have more questions. I find the
Sorry.
estimation of beta very high level. If you can repeat with examples, please. I don't know what do you want this.
Uh, yeah, MT and Umang both wants us to take an example. Can we take like real numbers? So let's do one thing. Let's take two features and five rows.
Yeah, we
Just for example.
can. Yeah, we can take this particular thing. So let's say we have one here. Let's say this x1 and x2 are the two features. So let's represent it by some number. uh, then your beta is equal to x transpose x inverse x transpose y. So let's say your this is your x. Let's say your y is equal to let's assume some real values.
So
So if
here
we
we
have
have,
we
yeah,
have
we
five
have
rows, then
two,
yeah,
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 we have five rows in the data and we have two features, X1 and X2, and we have a Y column as well.
yeah.
So now we want to estimate the coefficients now. So we have to go estimate three things: beta naught, beta one, and beta two.
Yeah. So basically, if you want to go with this particular formula, what you need to do, first find X transpose. I think it's fairly simple. Just convert rows into column. Then find X transpose X. I think it's this is we can also do, but I think here it will take some space. Then you need to find the inverse. Now inverse, I think you need derivation to find the inverse, but in the Python and in R you can easily find the inverse. Now what you need to do, you need to just multiply it with the X transpose and then multiply it with the Y. So step by step, this is the thing that you take into the consideration moving this way. So I think if you take in numbers also, it is going to be the same thing. And but yeah, thing is that you have to do these calculations, and like even with the five rows also, it will take I think 10 to 15 minutes to find the inverse and all those things.
Also, there can be like two extreme cases. So first, one case can be what happens if X transpose X is not invertible.
Yeah. So this particular thing happens when your data have multicollinearity. So this is what we are going to discuss in the last lecture, the concept of multicollinearity. So multicollinearity happens when some of your data, some of your rows are actually means some of your features are going to predict some other features. So let's say we have x1 to x100, हमारे पास 100 फीचर्स हैं. Let's say x2 and x4 मिलके x5 को प्रिडिक्ट कर सकते हैं. इन दैट पर्टिकुलर केस योर ट्रांस दिस पर्टिकुलर inverse will not exist, means exact inverse will not exist. You may calculate pseudo inverse or something others, but yeah, that is not will be the your natural estimate. So when you will try to find estimate in terms of in when there is a multicollinearity in the data, your beta naught or beta 1 beta 2, all those things are going to be the very large values, and that is not the actual estimate. That is very bogus values, or you can say that very misleading values. That is why in that case, when X transpose X inverse don't exist, we use some other thing. Especially we go with the Rees lasso, or we may use PCA regression. So what we do, we may transform the your predictor variables into orthogonal component, so that they are uncorrelated with each other. So that we can, I think, talk in the last session, like how to deal with
Also,
multicollinearity.
what happens if we have more features than the number of rows?
If you have p is greater than n, so that is entirely the, I think, separate thing, because this is case of big data. Like in the big data analysis, we learn like how to deal with some data like this. So that is a entirely different thing, and there are different methods for that. But yeah, in that case also you can use I think ridge regression, because ridge or lasso you can use both the thing, and that will do the work. But yeah, for that we have some other method in the high level. But yeah, that is very unnatural case. That is very absurd case, and that is dealt separately. Now,
Okay, so MT is still not able to understand the use of adding the ones.
so I think let me try once more and then. So we know that your models looks like something like, let's say in terms of two variables we are talking about, beta naught plus beta 1 x1. Okay. So if we have, let's say our y is, let's say y have n rows. Okay, means we have n values. हमारे पास n cross, let's say n cross 2 का n cross 1 का data है. So our y will be something like, let's say y1 y2 something like that, yn, and your x will be like x1 x2 something like xn, right? So if you want to write this particular equation in terms of matrices and vector, because your y is not a single quantity, we have n values of y. So how we will write this particular model in terms of vector and matrices? तो हम लोग क्या करेंगे यहाँ पे? So let's say this is our y. So our y is equal to, let's say this is our beta naught, plus we have beta 1 x1. So let's say we write beta 1, uh, then we have not this way, you can write okay, we know that y is equal to x beta plus epsilon. So if you write in this particular format, your x is going to be uh, and this your beta naught is going to be something like this, beta naught plus something like this. So if you write this particular in this format also, you have I think I'm making some mistake, I'll write here y. So y is equal to beta naught plus beta 1 x1 beta 2 x2 beta n xn plus epsilon. So let's say here e1 e2 something like that. But if you want to you can write it this way, but let's say we can also write it alternatively as we can write here 111 and then x1 x2 something like that xn, and what we do here, we here multiply by beta naught and beta 1. So if you just multiply it, you are still going to get the same thing that you have got here by writing the things separately. So writing one as a vector means that we are trying to concatenate each and everything in the simple single matrix, rather than writing different vectors for beta naught, writing different vectors for beta 1 to beta p, and then multiplying it, adding it, like we explained it the same way in the last slide also. So we just want to concatenate each and everything in the single matrix. That is why the simple way is to write here 1, and if you just multiply with beta naught and beta 1, it is going to be the same thing that you are going to get here by writing things separately. Now यहाँ पे हमें benefit क्या मिला कि we can estimate beta naught and beta 1 in a single equation. And what is that equation? That equation is beta hat is equal to x transpose x inverse x transpose y. So if you do this particular calculation, you get the estimate of beta naught and beta 1 separately, because we have assumed that our model is in this particular format that we are talking about. If your model in this particular format, then you cannot write this equation. अब यहाँ पे आपको इस equation में कुछ changes करने पड़ेंगे. And we are assuming that here we are not finding the estimate of beta naught, we are finding the estimate of beta 1 to beta k. So वहाँ पे सारे डेरिवेशंस भी डिफरेंट तरीके से चलेंगे. सो टू ब्रिंग ईच एंड एवरीथिंग ऑन द सेम इक्वेशंस, सो दैट वी डू नॉट नीड टू फाइंड द बीटा नॉट सेपरेटली, वी जस्ट concatenate वन हेयर, सो दैट कि वी आर जस्ट assuming दैट कि बीटा हैट जो वेक्टर है आपका, उसमें बीटा नॉट से लेके बीटा पी तक सारा एलिमेंट हम कंसीडर कर रहे हैं.
Sure. Let's move ahead.
Yeah, I think you can visualize it with a number. So you can take a x of, let's say, hypothetically five, let's say not five, three features, and y of five rows, and you can just take a random number by yourself, and you can visualize this particular thing. This will give you the same thing. So okay, so now once we have this particular thing, we can move to the practical section. So once we move to the practical section, we have here, like I have taken a medical insurance payout data, like I told you. So just 1 minute. So we will see this particular thing, and in association with this, we also have one more thing, like how to do hypothesis testing. But I think we will discuss it after this practical section, because this will be more interesting for you. So what we are going to do here, we are going to take a multiple linear regression data, and we'll try to fit the multiple linear regression. So this particular data is of medical insurance payout. So when you do pay for a medical insurance, how we are going to predict the amount that we are going to be charged. So let's understand this particular data. So this particular data have I think 7 columns. Out of this, the charge is what you want to predict. This is your y, and these are all your x1, x2, something like that. Now you can see that here some features are categorical, like this gender or sex is the categorical, male or female. Number of children is categorical, like 1, 2, 3. This smoker is also categorical, like either it can be a smoker or it cannot be a smoker. Okay, this region, let's say, is talking about some particular region like southwest, or maybe northeast, northwest, something like that. There are 4 or 5 region, whatever may be. So these, there are, I think there are few categorical columns, and there are few discrete values column also, like age. Then we have BMI. So based on all these things, can we actually predict what is going to be your medical insurance charges? So let's say just print the shape of the data. So actually the shape of data is 1, 3, 3, 8, 7. So we have 1, 3, 3, 8 rows. So last on the last session, we actually saw a data that has only 30 rows, but now we have more than 30 rows also. So like yesterday I explained you, there are two ways to import data in the Colab. So the first way is to either you can import the data using uploading here in your current runtime, or the second thing is you can also upload the data in the Google Drive. And once you upload the data in the Google Drive, you can mount your drive. And once you mount the drive, you can access your data by specifying its path on the drive. So we have uploaded the data on our drive, and will also share the data with you, so that you can also replicate the same experiment by yourself also. So what we're trying to do, when we just run the code, will try to mount to the drive, and we'll try to access the data from the drive itself. So let's run the code. Yeah, the runtime is connected. So once you try to run mount this server, it will ask to you for the access of the drive. So what you need to do, click on this connect to Google Drive, and just click on the your Google account that is associated with your drive on which you have kept your data. And when you will allow that particular thing, it will mount your drive in the current directory. Once your drive is mounted, you can access your data by specifying its path, like where your data lies. So my data lies in the my drive folder, then the dataset folder, then I have this particular expenses.csv. So once you mount the drive, I think the process is slow, but it will mount. You can just use read.csv to read the data. Now once you read the data, what you can do, use head method to print first 5 rows. So now we have mounted, just run this particular code. It will read the data, then data.head will give you the first 5 rows. And you can get the shape of the data using data and data.shape. Now the thing is that we have the dependent rows variable as the charges. We want to predict the charges based on all the other predictor variables, and we will also print the data.info, which will show you what is the some information about data, like how many of them are the missing values, what are the feature data type of particular columns, like it is integer, object means it can be a character based, float, integer, something like that. But the thing is that once, if you want to use your categorical data, this particular thing should be converted into the numbers. It's not like that you are going to use this particular thing as it is. So let's say we may do one thing. Let's say we give male equal to 1, then female can be represented by 0. So if we encounter 1, we say that it is a male, or 0, it is a female. Similarly, let's say yes, we can give 1, no, we can give to 0. Southwest, northeast, there are also different columns for this particular thing. So what we do, we will convert this into a dummy variable. But before than that, let's understand a particular thing, which is, let's say a particular column have 4 different unique values. So like northeast, let's say they have northeast, or let's say northwest. Then you have southeast. So we have a column that we have something like that, okay, and southeast. So if you want to convert this particular features into numerical values, one way is to, like assign a number. So let's say we assign a 1, 2, 3, 4. But the thing is that there is no natural ordering in this particular categorical value. It's not like northwest is higher than northeast. That is why we are going to give it 2, or maybe southwest is higher than the southeast. We are going to give it a 3. It's not like that. These are just the nominal variable. There is no any ordering within these variables. So what we do, we create different columns. So like based on these 4 features, we can create 3 different columns. So one may ask, why do we create 3 different columns? Why not 4 different columns? So let's understand how do we create the different columns. So one, we may create a column for the northeast, and if the person belong to the northeast region, we give it a 1, and if a person belong to the not belong to the northeast region, it will give it a 0. So we'll have 1 0 1 0, something like that. Similarly, we can do for the northwest. Similarly, we can do for the southwest. But let's say all these northeast, northwest, and southwest are all 0. What does it mean? It means that the person does not belong to all these 3 things. So by default, he belongs to the southwest. That is why we do not write separate columns for this particular thing. So let's say if you want to convert gender into 0 1, it's not like that. We create a column for male, give it a 1 if the particular person is a male, and we create a different column for the female, and we give it a 1 if the particular person is female. We don't do like that. What we do, we just give 1 to the male, and by default we assume that if it's not a male, then 0 is going to be assigned to the female. This is also true in the case of multiple categorical features. So we have 4 features. So based on that, we create 3 columns. So in general, if you have p category in a particular column, you create p minus 1 different columns if these p columns are not ordinal. Ordinal and nominal are 2 different types of categorical data. Ordinal means that there is some order in the data where this is not present in this particular thing, and nominal means that there is no particular ordering, which is the case here. So I think this should be clear for this particular thing.
MT has a question. If X female is 0, what's the use of having it in the data? Because B product X female will be 0.
Yeah, it means that if there is no particular effect of this particular having female of the particular beta. So you have raised a very right question. So let's say we have y is equal to beta naught plus beta 1 x1 plus beta 2 x2, something like, let's say x1 here is the categorical data. So if x1 is 1, then you have beta 1 here. So your y is going to be beta naught plus beta 1 plus beta 2 x2. And if x1 is equal to 0, your y is equal to beta naught plus beta 2 x2. So what's the problem? Like if you have specified x1 as the categorical thing, that is how your beta 1 is going to be estimated. If x1 is 0, then there is no effect of x1 on the y, and if x1 is 1, then whatever the effect is, that will be included in the terms of beta 1. So this is how the beta 1 have been estimated, because we earlier from the beginning we know that the x1 is the categorical column. So this is exactly the what you can say interpretation of any categorical features in the regression. If it's a 0, it means that we are not talking about its effect, like its effect has been discarded. And when this particular thing is 1, we say that whatever its effect is, it is included in the terms of beta 1. So it has been calculated in this particular term only. So there should not be confusion regarding if x1 is equal to 0, then beta 1 is going to vanish. Yeah, it is going to vanish, but this whole model is working in the same way. It's not like we are doing this. This is the categorical features, and that is why this particular thing is happening. Okay, if we just
So
move forward, there is a
so basically you see the relative impact of a
yeah,
variable.
relative impact. Yeah, exactly.
So for male, you'll have 1 into beta, and for female, you'll have 0. But you see relatively that male has uh, beta times more impact than the female one. So I had another question. So what happens if we create 2 columns out of the gender column? One for male and one for female. When male is 1, female is 0, male is 0, female is 1. This means that these columns are like linearly dependent because female equals to 1 minus male. So what is the uh, outcome of this?
So basically, if we just let's say create a column for male and column for female. So if male is one, this particular is zero, and if we have zero, this particular thing is one. So overall, this particular column is conveying the same information that this particular column is conveying. So your beta in general, when you try to estimate the beta, it will have a problem this X transpose X inverse that we talked about. This will be this will have problem, like this inverse will not be the accurate thing. That is why we do not include two separate columns. Like this column is conveying the same information that this column is conveying. How we have just represented male as 1 and female as 0. Here we represented female as 0 and male as 1. So these both columns will be highly collinear among each other. So that is why we do not do this kind of thing with our data.
So
This will,
exact inverse won't exist of that matrix, right?
yeah, I mean, it's not the exact, exact inverse won't exist. Some pseudo inverse may exist, but yeah, that this is because we are considering same columns twice. Same information is being used twice. It simply means that this X1 and this X2 features are highly correlated. There is multi-correlativity within the data.
Yeah. But I think this is not a problem in like tree-based algorithms because
Tree-based algorithm, it will work. In fact, tree-based algorithm also works if you just let's say give southwest as the 1, southeast as the 2, southeast northwest as a 3. It also work in that way because here
no,
we are just separating in terms of features. Like if southwest, the region is southwest, classify this particular thing in this way in decision tree, or maybe if region is southeast, do it this way.
so as far as I've worked with tree-based algorithms in Python, like decision trees, XGBoost, random forest, they don't take textual values at all.
Yeah, means
So,
it will not
yeah.
take text developments if we just give southwest is equal to 1, southeast is equal to 2. Like
Yeah,
I'm
even
saying
if
it, if
you
we,
take 1, 2, 3, 4, right? So the splitting of a node, it happens in such a way that let's say x greater than equal to 1 and less than equal to 3. So it takes the ordinal nature of it in in it, right? So x greater than equal to 1 and less than equal to 3. So that is also not accurate. So in that also we need one-hot encoding.
Yeah, means you will get some accuracy, but means the as the term of theoretically that is not correct.
Yeah.
Okay, so once we do this, what we can do, we use there is a function in the Python which is called get dummies. So what this get dummies do, it will convert all your categorical features into this particular way, like we talked by default. Means it will detect the categorical features and it will convert it this way. So if we'll just run this particular code and print the data, so just let's run this particular code, and if you just print the data here, once we convert it into the dummies, you can see that your data will be, so let the data to be printed. Yeah, your data will be something like this. So you can say that earlier we have a column for gender, but what it does, it takes the first value from the binary. Let's say if it's your column has only two variables, male and female, it will just make the column on the basis of the first variable. So 1 means male, 0 means female. Similarly, smoker, yes means 1 means yes, he is a smoker, 0 means not a smoker. Similarly, here we had the 4 different region, but yeah, we had only 3 columns. So 3 columns means that region northwest, region southeast, region southwest, and some other region was also there. But what does that mean? If all the particular things are 0, Here it means that that particular thing does not belong to these three regions, that is obviously going to belong to fourth region. And that is the what we earlier talked about, the relative effect you will see in the model, like there is no need to specify separately. But let's say if you want to specify, what we can do, यहाँ पे जो गेट डमीज में ड्रॉप फर्स्ट लिखा है ट्रू, इसको अगर आप फॉल्स कर दोगे, यू विल गेट टू कॉलम्स फॉर ऑल दिस पर्टिकुलर थिंग. So like sex male, sex female, smoker yes, smoker no, and all this particular thing. So let's if you just do this, so you can just try it by your own, but we will not consider that for our current work. So if we just do it that way, you can say that we have now uh, sorry, think oh sorry, we have run the data, we have to run the data from the beginning. So let's say if you want to see this particular effect, you can see by doing this way, and you can see that we have now separate column for each, both the thing. We have 2 columns for this, we have 4 columns for this. So that is,
Bratasi had a question. What do we do when we have nominal categorical values?
so like here we have children as a nominal, because 0 means no children, 1 means 1 children, 2 means 2 children. So there is a order. So you can use it as it is also, that will be okay with it. But we cannot use ordinal variable in this way. Like if you want to use ordinal variable in the nominal way, that will give
I
you
think
something
it's
different.
the opposite. I think she asked the opposite. I think nominal means there is no order. Ordinal means there is some
Yeah,
order,
yeah.
right? Yeah. Do we have one more question? Let's say you have a categorical column which has 1500 values, unique values. Should we perform one hot encoding or not?
So it depends actually. So let's say you have only 10,000 rows versus 1500 columns. That is not a good way to do. So what in that case we do? So let's say out of those 1500 unique values, let's say 10 values are such that they have they have more number of rows. They have very frequent occurrences. So just take 10 features for that, and others club as some other column. So let's say we made other features as others, just other features, and out of all those 1500, those which are not very frequent, let's say 1490 features are not so frequent, so we can club it into the some simple variable, and you can create 11 different features out of the 1500. But that actually depends upon the domain and what are the problem you're working on, what are the number of rows. So if you have 10 million rows, I think you can create 1500 values of 1500 columns, because 10 million rows के respect में 1500 predictors बहुत helpful होंगे predict करने में. But let's say if you have only 10,000 rows and some unique values are occurring very less number of times, let's say 1, 2 or 3 times, I think that is not a good thing to do. Isit, what is your opinion on this?
Yeah, so basically this is a general thing in classification or in regression also, that whenever you have too many categories, you just group them, try to reduce the number of categories. But yeah, as you said, it depends on the number of rows you have. Uh, if you have too much of data, it does not matter. But if you the number of columns in general should always be a lot lesser than the number of rows. In at least in the classical machine learning algorithms. Yeah, so just group the categories, try to reduce the number of categories.
So let's move ahead, because we have a lot to discuss and we already have passed the 1 hour. So once we have the dummies, we can calculate the basic statistics about the data that we talked yesterday also. And these always calculate the statistics for only the numerical column. So like these are the categorical things. So their statistics won't matter much, because maximum is 1, minimum is 0. So there is no need to see this particular main thing. This will be misleading. But for charges, your insurance charges, this will be important, because you can see your mean charges, your standard deviation of your payout charges, what is their median, what is its maximum. So these things can be helpful in general. But once we move ahead, what we do first, you can do a pair plot of the data. So what the pair plot does, pair plot takes, it will plot you a matrix of each variable against each other. So you can say that just let's come behind. You can see that this regional south northwest is plotted in terms of age. This regional northwest is plotted in terms of BMI. So this is the BMI of those people who actually does not belong to region Northwest. These are the BMI plot of those people who actually belongs to region Northwest. So this is just a plot to actually see what kind of relationship does exist between each and every variables. So I think this won't give you much information, rather we can use correlation matrix plot. So this is one of the plot that we use, and some idea of multicollinearity you can get from this plot, but not much. So what things you can see, so we want to predict the charges. So you can see that the charges has very high correlation with the smoker. So if a person is a smoker, I think the charges will be higher. So because this has a very positive correlation of 0.8 almost, not 0.8, 0.79, but it represent very high correlation. So also like with the age, you can see very high correlation, also high correlation with the charges. It means that as the age increases, the payout charges increases. So this is true in general. Like if you go and buy a medical insurance premium, and if you are a smoker, your premium charges will be relatively high because you have more risk of getting any disease than a non-smoker person. So these things, this small information you can get from particular thing, but you can see that this reason has no any significant correlation with the charges, because it does not depend on any particular reason unless and until that particular region has some other. So let's say there is a particular variable called disease, okay, and if it may happen that a particular person living in the southwest may have some particular kind of disease, so that disease variable will be a we can say that confounding variable which actually affects the relationship between this particular thing and the charges, but does not occur here. So you can see that high correlation means that that particular features have or something related to how we can uh, estimate the charges. So that is like a smoker, yes, is have a very high correlation with the charges. So that is going to be very impactful variable once we'll try to model the relationship.
Also,
So
the correlation matrix is always symmetrical. So you just need one side, uh, either below the diagonal or above the diagonal. You can choose anyone.
so this diagonal element is always one because this is the correlation between itself. So that is going to be always one. And you want to find correlation between any two variable you can see. So let's say you want to find the correlation between children and BMI. You can always find that. So like here is the BMI and here is the children. So this is the particular value of the correlation between children and the BMI variable. Sorry, this one. So you can always find this kind of information from the correlation plot. But let's moving ahead, what we want to do, we want to fit a model. So what we will do, we will separate out our y and x. We'll do the train test split, and here we are choosing test size to be 0.25, means 25%. And once you do this, your training data set have 1003 rows and your test data set have 335 rows. So once you do this, like yesterday, we first add a constant and we fit a model. So this OLS, I yesterday also explained that OLS means that ordinary least square, which is basically the regression using method of least square. So this is the same thing as the linear regression. So don't confuse it with some other model. So once you fit the thing, we have now the summary, and this is very important summary because we are going to get very different results. So we have R square and adjusted R square. You can see that R square is little bit high rather than the adjusted R square. We have this probability of F statistics, which is approximately equal to 0. It means that this model is highly significant. And then you have the particular estimate of the coefficient. These are the estimate of the coefficient. These are standard errors, and these are the p-values. So yesterday I told that if you have p-value of a particular what you can say predictor variables, if the p-value is greater than 0.05, or you can say alternatively p-value is less than 0.05, it means that your particular predictor variable is significant. So you can say that this particular is constant, we don't see. The age is significant, the BMI is significant, the children is significant, this smoker is significant, but this gender is not significant, this reason is not significant. So what does this particular thing means? This means that these four features are not contributing a lot in predicting your Y in this particular case. So this is why if you just remove these four variables and again calculate the regression, you are going to get almost similar R square and adjusted R square. So these four features are not significant also. When you will try to see their correlation with the y in the correlation plot, you can see that northeast have very low correlation with the charges. This smoker, sorry, age also, sex also has a very small correlation. This region also has very small correlation, but this smoker is very high. That is why it is significant. This age is significant because this age is also have very high correlation. Sorry, very a little bit high correlation. So this is what you also observe when you fit the model. So what we do, just as a sake of experiment, what we do, I remove these four features which are not significant, and we again fit the model. So I again fit the model with the same in the same way. So right now we will have only four features. If you remove all these features, we'll have only four features. So this, and this. So if you just make the regression, you are going to get the same adjusted R square, same thing. You can see that here. You just plotted with the four features only, and you got the R adjusted R square of 74.3. And if you just go here, here you will also see you have adjusted R square of 74.3. Sorry, here. So it means that if your variable is not significant, if even if you remove it from your regression model, it won't affect much of your variability in the model. It will just, your model will be still be able to explain a lot of things with the rest of four significant variables. I think it is a very big point because in the general, what we do, we just fit the model and we make predictions. But the thing is that if a particular variable is not significant, you can always remove it from your model. So I see you want to add something from your side.
Not really. I think you explained it really nicely. What are these last two columns after P greater than T?
Yeah, so these particular two columns are basically, these give you a confidence interval. So this what you can see, let's say these are your this is your estimate of your, let's say, age. Okay, so if you choose alpha is equal to 0.05, then we know that in the, when you do hypothesis testing, we say that, let's say, beta j is equal to 0, and your alternate hypothesis is beta j not equal to 0, right? So once you have here two tailed hypothesis, so what you can do here at alpha by 2 and here at also alpha by 2, you can calculate these two values. So these are those two values for a particular thing.
Yeah.
So
we have some questions. What do we do when we find multicollinearity? Do we need to drop the columns? So for example, charges and smokers.
So no, you just interpreted it wrongly. Like charge and smokers does not have multicollinearity because charges is your y, it is not your x. So this is good because if your any predictor variables x1 to xp, if these have high correlation with y, this is a really good thing because that feature predictor variables will be able to estimate y more clearly, or you can say that more mathematically. You have more surety that x1 will have impact on y. So multi-correlativity means that when x1, x2, like these have correlation among each other. If these have correlation with y, that is a very nice thing. You saw na कि smoker has 0.8 means 80% यहाँ पे 0.8 की correlation है, और that is why when you just plot the model, you can see that yes, this smoker is a highly significant means this is very significant. So इसको हम लोग y के साथ correlation नहीं देखते multi-correlative, हम लोग x, let's say अगर x1 to x5 है तो हम लोग देखते हैं कि क्या x2 x3 मिलके साथ में x5 को तो प्रिडिक्ट नहीं कर रहा, या फिर x4 को तो प्रिडिक्ट नहीं कर रहा, क्या x1 और x4 मिलके x2 को तो प्रिडिक्ट नहीं कर रहा. तो वी सी रिलेशनशिप लाइक दैट वे. ऐसा भी हो सकता है कि x1 x3 और x4 मिलके x5 को प्रिडिक्ट कर रहे हो. सो वी सी रिलेशनशिप, द कोलिनियर रिलेशनशिप अमंग प्रेडिक्टर वेरिएबल्स नॉट विथ y. So this is very confusing. Means it's not with the y. तो चार्जेस जो है हमारा यहाँ पे y वेरिएबल है, तो उसके साथ अगर हाई कोरिलेशन है प्रेडिक्टर्स का, दैट इज गुड थिंग. बट हमें x के रिस्पेक्ट में देखना है कि हमें उसको रिमूव करना है कि क्या करना है.
So for example, if x1 plus x4 equals to x5, then
Not necessarily x1. It also depends. Let's say alpha one is some constant. Alpha one times x1 plus
yeah,
alpha
any
two
linear
x2. Yeah,
combination,
linear
yeah,
combination is equal to x4. So this
then
may also happen.
x
Yeah.
x1 and x4 will have a high correlation, and x2 and x4 will have a high correlation, and x1 and x2 will also have high correlation. Is that
So
right?
this relationship, if one cannot get from the correlation itself. So ऐसा इसमें क्या होता है कि let's say x1 और x4 का जो correlation है, let's say 0.3 है, it's still not that significant. Let's say x2 और x4 का correlation 0.4 है, it's still not that significant. But ऐसा हो सकता है
Hmm.
कि ये दोनों मिलके जो इनके दोनों का मतलब ये जो रैंडम वेरिएबल्स आएगा इसका कोरिलेशन लेट से
Right.
0.9 हो, ऐसा हो सकता है. So the correlation is not the ideal way to detect multicollinearity. This is not the ideal way. This is just a way to see
Hmm.
कि अगर two features में correlation है कि नहीं. So this is just you can talk about two features x1, x2, x5, any number of two features, any combinations. But in general देखने के लिए कि क्या मन कौन सा ऐसा वेरिएबल है जो मल्टीकोलिनिटी से इफेक्ट मल्टीकोलिनिटी क्रिएट कर रहा है, या फिर कौन ऐसा है जिसको हम लोग अगर लें तो उसके हिसाब से हम बाकी सारे फीचर्स से उसको प्रिडिक्ट कर सकते हैं, ये इससे पता नहीं चलेगा. लाइक देयर इज सम अदर
Hmm.
मेट्रिक फॉर दैट, एंड दैट वी विल डिस्कस इन द नेक्स्ट सेक्शन.
Because uh, if you just look at this equation alpha 1 x1 plus alpha 2 x2 equal to x4, it might seem like x1 and x2 must be highly correlated with x4, but it might not appear in the correlation matrix because
Yeah.
when you change x1, you are not keeping x2 constant. X2 is also changing, so that's why the
Yeah.
resultant might
Hmm.
not be correlated.
Hmm.
So
So
if there
just
will, if, yeah,
I was saying that the correlation coefficient just give the linear relationship between two variables, not more than two variables. So we
yeah,
cannot talk about कि अगर तीन features मिलके एक साथ है, चार features मिलके या फिर any number of features मिलके किसी particular variable को predict कर रहे हो, we cannot find that particular thing with the correlation coefficient. So in general मैं एक थोड़ा high level idea देता हूँ multicollinearity में क्या करते हैं. If we detect there is a multicollinearity, one way is to remove the variable, but वहां पे क्या होता है, let's say इनके बीच का कोरिलेशन 80% है, बट स्टिल इफ यू रिमूव x4 वी आर गोइंग टू लूज 20% ऑफ द इंफॉर्मेशन दैट वी एक्चुअली मे हैव गॉट फ्रॉम द x4. सो वहां पे फीचर्स रिमूव करना इज नॉट एन आइडियल वे. सो देयर यू कैन यूज रीज एंड लेसो. सो आई विल एक्सप्लेन टुमारो कि हाउ रीज एंड लेसो एक्चुअली used to, not tomorrow in the next section. So how रीज एंड लेसो actually used to deal with the multicollinearity, why actually रीज एंड लेसो work with the multicollinearity. सो उसके लिए पहले वी नीड टू अंडरस्टैंड कि मल्टीक्युलिटी में फंडामेंटली क्या गलत होता है हमारे मॉडल के साथ. सो दैट ऑल द थिंग्स वी
hmm.
विल लाइक रिवील इन द नेक्स्ट सेशन. सो यहाँ पे once you have the model you can also predict for the test data like we did for the last session. So I think that is the one of the tasks that you should do by yourself. One of
I
your
think
tasks.
we'll have to cover hypothesis testing in the next session only because
Yeah,
we
we
have
will.
some more questions. So let's take
Yeah.
those. Can we design a correlation matrix which can list out the variables having higher correlation on its own?
Uh,
Yeah, I think you can do anything in Python. If you can work with Seaborn or matplotlib, you can plot anything. So yeah, it is possible. I don't think there is a library that can do that for you. I think you'll have to code it on your own. Right, Nitin? Yeah.
Can you design a correlation matrix which can list out variable having? Yeah, you can do this. Like there is a very simple thing. Once you have the all calculated all the correlation, you can just use any loop to just iterate each through, and let's say you fix a correlation of 0.8. If any particular variable is greater than 0.8, just list it out. You can do that.
Yeah. Are we going to be penalized in finding R squared adjusted if there are too many categorical variables? Do we have to drop them later on?
I think R square adjusted R square is not calculated in terms of categorical variable, but these are calculated in terms of Y. So like adjusted R square का formula मैंने last time भी लिखा था. It was 1 minus n minus 1 mean square error upon TSS. So this all does not conclude any X. Here यहाँ पे बस हम लोग Y के बारे में बात करते हैं, सब Y से calculate होता है. तो उसमें categorical features हो कुछ भी उससे we don't have any effect on the adjusted R square.
Then are these coefficients adjusted for type 1 error inflation?
I don't know what this particular things mean, but see, whatever the calculation we are making based on the assumptions that we made earlier कि हमारा जो error term है वो normal 0, sigma square है. So I don't know what this type 1 error inflation means, but
Type 1 error usually means false positives. But here this is a regression problem.
yeah,
So
that is
false
what I.
positive is in classification. So that is not relevant here. We can use PCA to.
Yeah, if we can use PCA in case of multi-equality also, because PCA will give you those features which are independent of each other. So those are highly uncorrelated features. So PCA works with the, what you can say,
Yeah,
this.
but yeah, that is a good technique to solve this problem. But one con of this is you lose the explainability,
Yeah.
because linear regression is mostly used because it is explainable. You actually get the weights of each feature. But in PCA, every independent feature is a combination of all features with different weights. So that's where you might lose some explainability on that. Outliers
So
treatment is necessary.
yeah, outlier treatment is necessary because like this kind of thing like outlier analysis, this we do specifically in residue. There is a separate chapter in the regression called residual analysis, where we check for outliers, and there is a special formula like Cook's DS statistics. Then we have a bunch of 4 or 5 different formula to calculate if a particular variable has any impact as outliers or not. But I think in general, people these days especially scale the data, do something before fitting the model, so that they take care of. But yeah, outliers have effect on the regression model. How? Let me show you something. So let's say this is your regression model, and these are your point that you have on the line. Now let's say you have one point, let's say here in the particular data set. So if you are going to calculate adjusted R square, this point will have impact on the this particular metric that you are going to calculate. It may be misleading because of this only point. So these kind of things we do because outliers may like your line may be the same, but your statistics may be the different. So these kind of things need to be deal with, and like there are many ways to deal with outliers in the
Line is
machine
also
learning.
not the same, right? The
Yeah,
line will
line
also be affected.
a little bit will be inclined toward this.
Yeah.
One
Yeah.
one more thing will be like, let's say your like let's say your uh, just extend this particular line. What I wanted to say. Yeah, like you have to understand the outliers will always impact your model also and these statistics also. So yeah. So I have one more thing here just for the quick, just if you want to use polynomial features to fit on the model, you can always use the polynomial features. So there's a library in the Python called sklearn preprocessing import polynomial features. So if you just define degrees equal to 2, it will fit the regression model of for these variables up to degree 2. Up to degree 2 means, okay, let's say if you have two variable x1 and x2. So in this model, you will have x1 square, x2 square, then x1, x2. So this is called, I mean, these are the, oh, sorry, x1 and x2 will also be there. So x1, x2, x1 square, x2 square, and this is called interaction term. So this will always also be there. So you are actually fitting the regression model on all these particular features if you are considering degree is equal to 2. So if you consider degree is equal to 3, you will have more number of features combining 2, 3, and having cubic powers square, something like that. So just I have fitted up a small model on this just for the sake of simplicity. And you can here see that you have your R square adjusted by at least 10 point. Earlier you have 0.74, but now we have 0.84. So your R square, adjusted R square has been increased. It shows that some of your variable may have some quadratic relationship with your Y. So that is why adjusted R square is acting better. But yeah, also here you will find a lot of insignificant variable also, like these are all insignificant. So this is significant, 0.05 से कम है. These are all insignificant. Then again, this is significant. So these kind of things you can also try with any kind of data. If your linear model have some adjusted r square, you can always go for quadratic and see what is the adjust values. If your some of your variable have some quadratic or some other relationship with your particular y, your adjusted r square will actually be improved on that. And you can also see that your f statistics is 0. So this f statistics 0 means that your regression model as a whole, but means we are not considering about some particular variables which are not significant. You can always remove that, but your regression model as a whole is significant. So this is one of the things that we find out from the probability of statistics. So it should be less than 0.05 for your model to be significant.
So in
So
the
this,
if you scroll down, you see the list of variables and their significance, right? So
yeah, means
how
this
do we know? Yeah, how do
uh,
we know which variable is x10, which is x12?
so like this polynomial features have some pattern, like how they convert. So what we do, let's say if I have x1 and x2, so how do they convert? Maybe they put x1 x2 first, then there is square term first, then the interaction term first. So first of all, when we are trying to convert them into polynomial features, we need to see that pattern from the documentation of sklearn, and then we may name our column based on that. So but यहाँ पे मैंने simplicity के लिए बस दिखा दिया, but that is the main point behind doing that. As you can see, and you will actually get x1 square, x2 square, x3 x2 का combinations ऐसे ऐसे.
Yeah.
But अगर तुम नीचे आओगे देखोगे यहाँ पे कुछ variables zero है. तो what does this particular thing mean? So let's say कि अगर हम हमारा x1 यहाँ पे age है, sorry age नहीं है, smoker है, तो उसमें 0101 value है, right? और let's say x2 हमारा यहाँ पे what you can say और क्या था वेरिएबल हमारा, स्मोकर एंड जेंडर है यहाँ पे, ठीक है. दिस आल्सो हैव 0101. इट मे हैपेंस दैट कि सम x1 and x2 हैव काउंटर इंट्यूटिव वैल्यूज, लाइक यहाँ पे 0 है तो यहाँ पे 1 है, यहाँ पे 0 है तो 1 है. तो अगर आप यहाँ पे x1 x2 कैलकुलेट करोगे प्रोडक्ट इंटरेक्शन टर्म का, दिस इज ऑल गोइंग टू बी 0. सो यहाँ पे दो ऐसे कॉलम्स क्रिएट हुए होंगे जिनके सारे कोफिशिएंट ही 0 हैं. दैट इज व्हाई दिस टू थिंग्स डज नॉट मेक एनी सेंस टू अस. सो ऐसा है कि जब व्हेन वी क्रिएट पॉलिनोमियल फीचर्स, वी फर्स्ट सी आवर फीचर्स. अगर कोई जीरो है पूरा कॉलम सी, just drop it, that is not of our concern. But yeah, in general, polynomial, like this polynomial quadratic model, like we have seen up to quadratic, these things also work in the, this will generally increase your r square, adjusted r square by few point always.
These will also always be the interaction terms, right?
Yeah, there is always interaction term, means so maybe x1 to x5 में interaction term हो सकता है. So if both are let's say real values, ये age है और let's say ये BMI है, so this is not going to be 0. but अगर कोई categorical है दोनों और values कुछ ऐसा हो गया है कि 1010 का combination हो गया है, so वो all 0 हो गया, तो फिर वो पूरा मतलब estimate, वो your estimate will not be there. That is why we get something called nan and something like that. It's not a number. This is something, some infinity or some maybe other values. So guys, I think we have taken a lot of your time, but this was all from my side for today. And in the next session, we'll start with hypothesis testing and covered the the multi-quantity also.
Any other questions? Anyone?
I think people want to go.
Yeah.
So thanks guys for joining. That was from my
Thanks
side.
everyone.
Thanks,
so next session will be on Friday.
Yeah. Means mostly will be on Friday, but if there is some change, I think we can always convey it to the other people.
Yeah, you'll get an email, everyone, whenever this next session will be, probably on Friday, but if not, then probably on the weekend or next week maybe.
Yeah. And we have all the recordings of this session, so we will send the recordings towards the end only, because that will be easier for us to manage.
Yeah. After the 3 sessions, you'll get it. Will we have such classes on all ML algorithms? Yeah, of course.
We will try to extend it. Yeah. We will try to also include session for the Python, NumPy, Pandas, and all the other things. So this was just for we were starting. That's why we had to start with somewhere. So that's why we choose Regression to start. But yeah, we will ultimately be escalating this particular thing in general.
Yeah. All right.
Okay,
Thanks,
then all
everyone.
the best to everyone.
Um,
Thank you. Thank you, Isit. Bye bye.
Thanks, Nitin. Yeah.